both Bhaskar and I, who are been part of this whole project. Sir, 10 minutes, can you wait? 10 minutes. Let us see something very interesting that we are. Were actually communication engineer and not power engineer. In fact, I did not know some of the facts about the fan. We will talk about it. We got into the area of power because when we used to go to the villages to try to install our telecom system, the only reason our internet cafe would not work is because of not having power. And our backup powers and this and that, and we're tired. And Chennai city was another place where we're suffering. And two of us kind of were pushed around, sort of saying, let's start working on power. There was one colleague of ours, Dr. Kumarvel, he was working on solar, and he kept on saying, come and solar will do a very interesting thing. So we started working on solar. Actually, I'll tell you in about 5 to 10 minutes, very quickly, some of the things that we went around. And I think we are very lucky with what we have come across. I think purely luck. I wish I had read that article earlier. But basically, let's talk about shortage of power. Shortage of power, India understands. But still, when we started working on it, we wanted to quantify shortage of power. And we very soon came across what is called power exchange in India. There are this power exchange where the producers of power sell power to the consumers of power. Consumers of power are the state electricity board. And we saw that every day the price goes from 2 rupees to 4 rupee 50 every day. And basically came to the conclusion that 2 rupees is when there is surplus power and 4 rupee 50 paise when there is a shortage of power. Every day it happens. You open pretty much 450. We also actually figured out, well, 2 and 450 is not that bad. Why does the electricity board keeps on crying? Then we actually found out this was the power at the source of generation. By the time you bring it to and sell it to a consumer, you have to add 50 to 60% more costs. So the price start going up. And then little bit of research shows us that many days the prices shoots up to 12 rupees. And that's where the shortage started reflecting. By the way, this 12 rupees was about 2.5 years back. Last year, consistently in November, December, the prices have shot to 20 rupees per unit. Per unit prices. 20 rupees is the power at the source. By the time it will be delivered, it will be 27, 28 rupees, and we pay much less. So this was a picture that we got, and pretty much whatever people say, now we have surplus, we won't do this. Pockets here, there, rural areas as you go, power cuts are very large, and this is what we started looking at. Then the next very important thing, and this partly I'll sort of say my stint in State Bank of India for 6 years as a board member gave me to do computations of a different kind. And one, of course, I started looking at what does it cost? What does it cost a consumer? Grid, of course, we knew all the way to 4 rupees, sometime even 2 or 3 rupees, but 4 rupees per unit to 9 rupees per unit. Because this research park was paying 7, 8 rupees. Otherwise, I would not have known that it goes up to 9 rupees per unit. This is the cost per unit of power. But as soon as, for example, power fails in this building, we turn on the diesel generator. We are actually paying through our nose in this research park. And I started looking at why. And suddenly we found the reason is diesel generator, because power cuts takes place plenty of time. And unbelievably, when I calculate the total cost of power, it came to 24 rupees. That is including the cost of the generator, the interest, depreciation, the maintenance, operations, but also the other interesting thing that we found, the generator does not run at the full capacity all the time. And if it ran at 40% capacity, it went up to 34 rupees. And as soon as we sort of say, well, we are paying that, and nobody recognizes that. All of us pay that. We don't make protest on that. Whom do we protest? I don't know who will protest to. Then I thought batteries will save things. UPS, all of us in our rooms have using battery. Again, I calculated the total cost of the power for the battery. And I found for per unit of power, it cost a minimum of 12 to 15 rupees. Actually, higher than that. 12 to 15 rupees is an underestimate. I have not taken the cost of a charger into account. And then it costs at least 5 rupees to charge. So again, you are talking about 17 to 20 rupees. So, and this is the time when we started working on it. We actually sort of said, well, if I put solar on my roof top, I don't need transmission and distribution losses, because I'll directly get it in my building and directly use it. And we actually did that, and we found that if I directly use DC, it will come to around 5 rupees to 5 rupee 50 paise per unit. Again, taking into account all the long-term this thing. As soon as I convert to AC, I add another rupee. Not too bad, but 1 rupee I add. But I sort of saw that at 550, of course, is comparable to the best that I can get from the grid. And we realized that that is the way to go. But the question came, but solar do not always work. I mean, when the cloud comes, solar is not there. And on power cuts, it will not work. So what is an answer to it? Where is a pull for the citizen? Why will citizen go and put it? That was a question that we had particularly for homes. And then we came across this DC. One interesting thing, of course, lighting is the first thing that we came across. We are moving towards DC, and DC LED consume very little power, about half to 1/3 of the power of the CFL bulb. And we typically can make a very nice tube lights like this, 15 watts it will take for LED. But we actually recognize this, that if I take 15 watts of AC, 230 volts, and then convert it to DC, because the LED only works with DC, my efficiency is very low, 50%. So I'm actually wasting all the power in the conversion. So this whole AC with LED doesn't really give me much benefit. It gives me 15-20% benefit. If I could directly bring a DC line, it will help a lot. So this is the first thing that we actually recognize. And the second thing came as a shock. I don't know how the technology has evolved since early 1900. We should trace it. But today, a brushless DC fan, not the old DC fan, a brushless DC fan came into being because of the power electronics revolution of around 2002-2003. One of our alumni apparently came with this IGBT, which actually enabled something like this. It consumes about 40% of the power of a AC fan. A typical fan consumes 70 watts, a DC fan consumes only 30 watts. We were shocked. We started working with the same company, Crompton Greaves, to make a DC fan for us. We actually helped them manufacture this. And today I have got plenty of these fans. They work 30 watts. What is more interesting, that when I run it on the lowest power, on speed 1, the AC fan still consumes 60 watts. The DC fan consumes 7 watts. On speed 2, AC fans consume still 63 watts. DC fan consumes 15 watts. And at full speed, it consumes 30 watts. And we suddenly realized, well, the same kind of efficiency is possible probably in refrigerator, in air conditioner, and we have started working on it. For example, we have just now building AHU here for this building, and we are seeing that we straight away get about 40% higher efficiency for the air handling unit for the air conditioner. And then electronics, that we knew all works on DC. Low power electronics, and when we convert AC to DC, I was shocked. I am using this HP, very latest laptop, has a 60% efficiency, 40% power goes. Similarly, when I use a cell phone, 60% power goes. Nokia phone, 40% is used. And therefore, the question started asking, world switched over to AC power for transmission. Has time come to switch it, at least at premises? The problem is, again, where is the pull to? You have to redo the wiring, you have to redo. How does one go about doing this? So these two things were hitting us. And Dr. Uma Shankar, who is also happened to be our alumni, who was the power secretary, we came here to this very room, and we had a presentation for him. He actually was shocked, but agreed with all the things that we had told him. He says, but where is the pull? If you need to create a pull, and you need to solve a bigger problem, power cuts in India. Power cuts is so bad in India. That is what you really need to overcome. So we had no answer, of course. Basically, he said, can you provide some minimum power to each home, even in adverse power situation? You solve that problem, bring your DC and solar along with it. And we had no answer. But I think from there onwards, we stopped, and it took us 2.5 months, exactly around this time, February of last year to April. And suddenly, one after another, we're able to solve a problem. And we're lucky to come across a solution where we sort of say, on the existing network, existing grid, we can provide a limited amount of power to every home, even in load shedding. What are we doing? Basically, the power cuts are controlled by the substation, 33 kV substation. That is the place where supply, when it exceeds demand, the power is cut. Very simple. That's what it is done. When total supply exceeds demand, in some areas, 33 kV substation cuts power or does load shedding for individual lines. The basic thing that we sort of said, can we allow a small amount of power to continue to flow, 5 to 7%, maybe 10%, and cut 85%, 90%, cut 80, not 83%, 93%, 95%. We came with the concept of brownout instead of blackout. Can we bring in a brownout instead of blackout. Can we do that on existing grid? It should be small enough so that even in the worst power situation, not more than 5, 7, 10%. We are not talking about 20%, because 20% may not be available. So it is not 83%, it's 93%. Then this freed brownout power, it has to be distinguished from the normal power. Otherwise, it will be used like a normal power. So we say, well, finally we came to the conclusion that we'll do it at a very low voltage, 90 volts instead of 230 volts. It cannot be used in a normal situation. And then use this with energy efficient devices at homes. At home, separate it into 2 lines. One where you will put this kind of, and separate it and use it for energy efficient devices. So that's actually the idea that we came about. Now what did we do? So basically this is what we did. A 33 kV substation, whenever this is where the blackout switches are there, or load where the power cuts takes place. Whenever supply exceeds, where supply is less than the demand, the power cut takes place. We said instead of blackout, you will do a simple thing. One simple replacement. Take either a tap from an existing transformer, add a small transformer, bring down the voltage by a factor of 2.5, draw only 5 to 7% of the power, and feed it onto the line. Now there will be low voltage therefore coming, very low voltage coming. Now with the low voltage, industry will cut it off. Normally there is a low voltage cutoff they will use, and they will cut it off. At homes and offices, you will get the normal voltage and this low voltage. What do you do when you do come to at home and the low voltage? At home and low voltage, you will get this input, but you will supply 2 outputs. One at 230 volt AC, but this will be unlimited power. This is like current power. Plus you will provide a second line, which will be 48 volt DC. It will be limited but uninterrupted. The important thing, it will be a limited power but uninterrupted. And this uninterrupted power will be used with DC devices. So therefore even the small power looks large. It can go long distance. It can actually connect to many, many more devices. And it's basically the devices that we are looking at, lights, fans, and electronics, including television. Television is electronics. So essentially this is the idea that 230 volts come in. This is a 4.4 kV step down for the distribution transformer comes in, and 2 more minutes comes through existing smart meter and come to 230 volts. Whenever there is a low voltage, the AC line trips, simply because it detects a low voltage detector and trips. But in either case, whether it's a normal or low voltage, you put a programmable DC unit and you put a 48 volt, 100 watts and feed this. Now one will say 100 watts? What can 100 watts do? Well, we then actually started installing, and we say 3 lights, 2 fans, 1 cell phone charging, it can do quite well. Alternatively, it can do 3 lights, 1 fan, 1 television, 1 cell phone charging. You can shut off 1 fan and turn on the television. Not bad for the lowest income homes. At least we are providing minimum 3 lights, 2 fans, and cell phone charging, or 3 lights, 1 fan, 1 LED TV or LCD TV, and a cell phone charging. And it can be installed incrementally, one by one. And then 100 watt is small enough such that even if every home draws the full 100 watt, it can be found even in the worst power cut. That's the whole idea. You could have made it larger, but then it wouldn't be available. But what if it wants more? It has created a pull for DC devices. That's where we added something more. We sort of said, well, since we are providing a DC power, if you want more, you just add a solar unit out there. And suddenly your 100 watts can become, and this can become 200 watts, 250 watts, 300 watts. You can put a small battery also out there. And once you have something like 225, 250 watts, you are going to be able to put 4, 5 lights, 4 fans, largish television, cell phone, laptops, tablets, and you essentially, even the upper middle class homes, your AC won't run, your heaters won't run, this thing won't run, but otherwise things will work. This is finally what we actually got, and AC will of course continue whenever there is no power cut, but when there is a load shedding, it won't do. So you can go now. I know that you have to go. So this is the basic idea with which we essentially did that. Well, 2 more slides just. Since then, we have been continuously innovating. So what did we do? We actually built the whole thing. We built it, first installed it in our lab, then we installed it in one demo home, and now we have installed in about 5-6 homes in campus, 3-4 offices, and everything we checked out working quite well. There is no issue in technically in terms of working. Once that got done, we kept on innovating in the meantime. How can we improve this? Can we do something better? For example, that's where Raman came in. And there are a few others who came in, sort of saying, we are building complex. Maybe we'll install such units in every home. We came one step further, saying that, well, if you are going to install in a building complex, we can probably do even better. Let's assume that your 11 kV line comes to you and you have a distribution transformer from which you get the 440 volts. It is here, instead of at every home converting the power to DC, we'll convert the power to DC at a single place for all the homes. So if there are 16 homes, we will convert 16 into 100 watts, little more than 16 into 100 watts. We'll also add a solar panel out here. Because now, for all homes, solar panel can be added, a small battery can be added, and maybe a AC-DC converter is also added, because when the AC power is there, you can actually draw that. And instead of 100 watts, you can actually give 400 watts to each outer flat. And if you can give 400 watts, practically I can't think of 400 watts DC, you can actually use anything more than that. 5-6 lights, 5-6 fans, couple of televisions, couple of laptops, cell phone charging, tablet charging, you can actually do that. And then we came across another very interesting idea, and in talking to some of the builders, so when you get this 11 kV line for the building, you need not even depend on the telecom, because depend on the electricity operator to actually do this load shedding and convert it to a 90 volt. You don't need to do that. You can tell them that give me a separate line. I will manage the load. Whenever you give me a message, I will switch over and draw only 100 watts per home. Whenever you say no brownout, I will go back to the full load. So essentially, you can very easily, you can do this, and at this point, you design a very simple unit, what's called a brownout messaging system. So you receive a message, you can even receive it as an SMS, you can receive it as an internet message. The second you get the message, you actually cut off the AC line. And then how a DC line, which is 100 watts per home, continue to work. Of course, if you have solar panel and battery, and all this can become 400 watts. The minute you say normal restored, you can go back, and AC line and DC line both can be done. This is what we actually are building, and we are hoping to install it in their place, in our own buildings, and I think we can actually make it such that no power failure really takes place. Now, I'll just take last 2 minutes, talk about some of the policy relevance. The first important thing about idea like this, something like this, it requires minimal investment for either government, that is, I'm talking about being the distribution companies, or the citizen. The existing meter have to have either a replacement meter, or you need a small unit at home, which is a AC-DC conversion. We estimate the price will be around not 2,500 rupees, that was in our old design, more like 1,200 to 1,500 rupees per unit. And you can also do, of course, time of the day metering, etc. Minimal change in existing power, incremental addition of devices, that's the main thing. It also generates a huge pull for these DC devices. Because now, suddenly, only with DC devices you can actually use this in an effective manner. So you suddenly create a market for DC devices. You create therefore these are energy efficient devices. This is something that anyway India has been wanting, but just have not succeeded. You also create a huge pull for decentralized solar production, because the solar enables you to add your power to 400 watts. So even upper middle class homes can have it. And even smaller homes can start putting smaller installation and do something like this. It of course can help you manage subsidy. Now the government can come and say, this 100 watt unit I will subsidize. The other one AC, I will let it go to market rates. Now if that happens, the whole power distribution company will actually financially buy back, and it generates huge citizen goodwill. Further, for housing colonies, policies that allow decentralized power generation, use energy efficient DC devices, allow them to use a limited power on receiving load shedding signal, this very thing that I described. Very simple change in policy enables you to start moving in a totally different direction. They are doing their own load management, but under your control. And you can make sure that they are doing it. If they are not doing it, if you find it is not doing it, you can actually withdraw that kind of facility. The other great thing that I see, in this manner, if you think of 100 million homes out of our 250 million homes can add about a kilowatt of decentralized solar, you are talking about addition of 100 gigawatt. Now 100 gigawatt is 40% of today's capacity. And this can happen in relatively very, very short time. So something like this enables you, what I'm trying to say, technology is open possibilities. That's one of the key things that we are trying to point out. And of course, you need a lot more R&D on new DC energy efficient devices. We have come up with some, but I think much more needs to be done. And finally, I'll sort of say, we need to really work on this electric vehicle. Because once you move away from this shortage of power situation, our biggest energy problem will come from oil. Because we continue to import, our oil bill has gone up by a factor of 8 times in last 10 years. If we continue to just do that, we are going to be in big trouble. So what I'm hoping is that really move towards electric vehicle. And I think by and large, the electric vehicle technology is well in our control. We can move there. There is not a shortage of electricity. I think it is almost in the situation that we can move there. We can finally gain rather than lose. A little bit of support, little bit of push, and we can get there. Well, that's all that I will say, and I'll stop there, and we'll have the panel continuing.